Okay, good morning. We have been discussing about air conditioning in the previous lecture. Let us continue our discussion on the same. So, in terms of air conditioning, I mentioned you that we may have comfort requirements or industrial applications of air conditioning, and depending upon the function, depending upon the season, and depending upon the distribution of the equipment, we have actually studied different classifications of air conditioning systems. Okay. Of course, whenever we were discussing all these classifications, we discussed in a broader sense. We did not go into much technical details of the system. So, in order to design an air conditioning system and in order to understand all the technical details of the air conditioning system, we must have the knowledge of properties of moist air, because ultimately moist air is actually the participating medium in addition to the refrigerating system which is used for processing of the moist air. Okay, so generally in our atmosphere we have dry air which mostly include many gases. If you talk about in atmosphere, then what is the composition by volume? 78 to 79% of nitrogen, 78 point something. So if we just do the approximation, then almost 79% by volume is actually nitrogen and 21% by volume is oxygen. However, these percentages are, for example, 78 point something and 20 point something, and then in addition somewhere close to 0.98% we have many other gases such as CO2, argon, helium, etc. Okay, so these are the remaining gases, and of course one important thing which typically is present in the ambient air, that is actually water vapor. Okay, and other than water vapor we see outside, maybe because of different things. For example, if some construction is taking place, then we will be having tiny dust particulate matter. Because of agriculture waste or biomass waste also, we will be finding some sort of solid dust and particulate matter will also be suspended in the air. However, whenever we are processing the air for certain industrial application and human comfort condition, our first criteria is that these components must be removed. So whenever we will be removing these components, then ultimately we will be having dry air and water vapor. Now if I talk about purely on human comfort condition, we cannot survive in a scenario where we have only dry air and there is no presence of water vapor. Okay, so ultimately for human comfort condition we say that humidity close to, relative humidity close to 54% or 56% is actually required. So it means that for different industrial applications as well as for the human comfort conditions, there must be some fraction of water vapor present in the air. Okay, so if in the dry air, which ultimately is a mixture of different gases, of course the boiling point of these gases is very low. Okay, so it means that for all the gases, nitrogen, oxygen, carbon dioxide, etc., we are significantly away from their critical point. So whenever we are significantly away from the critical point, it means their temperature is relative to their critical temperature, their temperature is very large. And we know from generalized compressibility chart in our thermodynamics that all the gases whose temperature is significantly larger in comparison to the critical temperature, they mostly behave as ideal gases. Is this one clear? So for all these gases, I can assume the ideal gas behavior. However, I do have water vapor present. Okay, so whenever I have water vapor also present, I also need to determine the properties of the water vapor. And we know that water vapor, of course, under certain conditions it can behave as an ideal gas, but entirely it cannot behave as ideal gas for all the temperatures and pressures. Okay, so that's why what we need to do, we need to properly estimate the properties of this moist mixture of dry air and water vapor. Is this one clear? So the study, particularly the science that deals with, or the thermodynamics of this type of moist air, is something which is referred to as psychrometry. Okay. Now let's talk about psychometric behavior. But before going into psychometric behavior, let us classify some of the common terminologies. Okay. Before that, whenever we do deal with the mixtures, there is one important law which is known as Amagat-Ledoc's law. So can you tell me what is this law? If you have mixture of gases, for example, I have mixture of gases, say A, B, C and D. So if I apply this law on the mixture of gases, then what I will be getting? It says that in this chamber, if I consider in this classroom, I have 4 different gases A, B, C, D. What I will be having? Of course, the room will be having some total pressure. Whatever the total pressure of the room will be there, that will be the sum of partial pressures of all the components A, B, C and D. And if mixture is properly mixed together, I will be finding that temperature of the mixture will also be almost the same. Is this one clear? So if I assume that I have same total pressure P and same temperature T, then if I segregate out A, B, C and D, what will be happening? Please tell me. Whenever all A, B, C, D are present as a mixture, say these are forming total volume V at pressure and temperature of P and T. Now, if I segregate all the gases such that the individual component is having pressure P and temperature T, what I will be getting? Right now, their total pressure will be nothing but partial pressure of A plus partial pressure of B plus C plus D. Right now, that will be forming the total pressure. But I am saying that if the partial pressure is made equal to P, okay, at the same temperature T, what will be happening? Right now, all the gases A, B, C, D were occupying the entire room. But when I am segregating gas A, then gas A will be occupying some lesser volume in order to produce the same amount of pressure. Is this one clear? So ultimately I will be finding that, say this is the VA as the volume of gas A at pressure and temperature of P and T. Similarly, VB is the volume of gas B at the same pressure and temperature. Likewise, VC and VD. What ultimately I will be getting? As a mixture, their entire volume will be V at the same pressure and temperature T. Is this one clear? So, Amagat-Ledoc's law says that if I maintain the same pressure for individual components as that of the mixture pressure and temperature, if I make same pressure and temperature conditions, corresponding to that, whatever the sum of their partial volumes will be, that will be nothing but equal to volume of the complete gas mixture. Is this one clear? Anyone is having any doubt about this? Please tell me. All are clear with this? Then next is Dalton's law. What Dalton's law says? What are the constraints now? Have you not studied Dalton's law of partial pressure for gas mixtures? Studied? So what it says? Yes. First point is volume and temperature has to be same. So if you maintain same volume and same temperature, then for the same total V, so this was a total volume and this was temperature. Say total pressure was P. Now if in the entire room, entire volume V and temperature T, instead of taking the entire mixture, here what I am having, A plus B plus C plus D, but instead of entire mixture, if I only take single gas A, what will be happening? Pressure will be less. Okay, so its pressure will be nothing but equal to PA. Likewise, in this, if I take only gas B, then pressure will be PB, PC, PD, and if mixture pressure is P, then it is for sure that PA, PB, PC and PD will be less than P. Okay, so the pressure of a particular component at same volume and temperature is something which is called as the partial pressure. This is the partial pressure. Is this one clear? At same volume and temperature as that of mixture, whatever the individual component pressure will be applying, that pressure is called as its partial pressure. Okay, and the sum of the partial pressures is actually given as total pressure, PA plus PB plus PC plus PD. Is this point clear? So these two laws are very, very important for deriving the properties of the moist air. Is this one clear? Now let's come to moist air. In moist air, I have two components. One I will be having water vapor and other I am having dry air. Is this one clear? Water vapor and dry air. So it means that in order to understand the properties of the moist air, we first know the properties of dry air, then we first must know the properties of the water vapor. And as a combination, whatever the properties I will be getting, that will be defined as the property for the moist air. Is this point clear? Typically, dry air at ambient pressure and temperatures nearby ambient can be easily treated as an ideal gas. And the reason for treating this as an ideal gas, I have already told you that why we are treating this as an ideal gas. High temperature in comparison to its critical temperature. Okay, so relative to the critical temperature, temperature is high. Relative to ambient, it may not be high. Okay, but water vapor, for water vapor, what is critical temperature? What are critical pressure and temperature for water vapor? $220 bar and 374 degree Celsius. Okay. However, in your air conditioning application, what is the range of operation of moist air? Pressure close to ambient pressure and temperature mostly in the range of 0 to 50 degrees Celsius. Whenever you are dealing with the cooling systems, then you will be operating close to 0. When you are dealing with the heating systems, then you will be dealing at max up to 50 degrees Celsius. Is this one clear? Anyone is having any doubt about this? Please tell me. All are clear about this? Then we have to check, because with reference to critical temperature, its temperature is very low. We have to check whether it can be assumed to be having ideal behavior or not. First point is clear. Second important point which I would like to emphasize is that generally for a pure substance, particularly a simply compressible pure substance, how many number of independent intensive properties are needed to determine the thermodynamic state? 2. That is what we study from state postulates. When I have a mixture, when we were discussing about vapor absorption systems, I told at that time that if we have a mixture, then what we need to do? One more property is needed. Now what is moist air? Moist air is again a combination of dry air and water vapor. So it's again a mixture. Okay. So as a mixture, because dry air itself is a pure substance and water vapor itself is a pure substance. Now two pure substances are actually mixing together and it is forming a mixture as a moist air. So it means for determining the state of the moist air, how many properties are needed? 3 properties are needed. Is this point clear? Anyone is having any doubt about this? Okay. Other than this, now let's come back to, for dry air, because it will be following ideal gas equation. So I can write pressure into specific volume is equal to RT, where R is gas constant. And what is the value of gas constant for air? 0.287 kilojoule per kg Kelvin, okay, or 287 joule per kg Kelvin. Is this point clear? Now we know that if we have some gas which is just following ideal gas behavior, then enthalpy will be only function of temperature. Is this point clear or not? For dry air, enthalpy will be strongly function of temperature. Okay. Now, this dry air is close to ambient pressure and ambient temperature, and mostly in air conditioning applications, we will be operating in the range of 0 to 50 degrees Celsius. Okay. So, for the range of 0 to 50 degrees Celsius, my specific heat of air, Cp of air, can be assumed to be 1.005 kilojoule per kg Kelvin. Is this point clear? So Cp is a fixed value, 1.005 kilojoule per kg Kelvin. Now, if I assume that, because for air conditioning I am operating from 0 to 50 degrees Celsius. If I assume that for dry air I have set my reference state at T equal to 0 degree Celsius, what I will be getting? Please tell me. If my reference state is T equal to 0 degree Celsius, what I will be getting? Let's assume enthalpy at this point is 0. Enthalpy of the dry air at T equal to 0 is nothing but equal to 0 kilojoule per kg. So this I have set as reference state. So now if I have to calculate enthalpy at any temperature T, can I simply write Cp times T? Enthalpy will be becoming equal to, because Ht minus H reference state, which is 0, equal to Cp into T minus T reference. T reference is again 0. So H I can simply write as Cp into T for my air conditioning applications. So the enthalpy of the air can be simply written as 1.005 times simply temperature, and unit is kilojoule per kg. All are clear with this point? Now let's talk about water vapor. If I plot temperature entropy diagram for water vapor, the range of temperature in which we are operating, that is less than the critical point, because this is my Tc. And as a whole, we are majorly interested in enthalpy, because enthalpy will be actually participating in different processes, and that too, whenever I am talking about the moist air, in moist air, my water will be always present in which phase? Liquid or vapor? Liquid phase. In moist air, water will be present in which phase? In this air, there is some water. It is in which phase? Vapor phase. Okay, so on this TS diagram, I must focus mainly on the vapor phase. So if I go to vapor phase, this is constant enthalpy line in the vapor phase. What is your observation? These are different constant enthalpy lines. For example, H1, H2, H3, H4, H5. And what are constant pressure lines? These are constant pressure lines. Okay. So in upward side my pressure is increasing. So when I am operating at nearly higher pressures, you can follow any of the line and you will be finding that enthalpy is both function of temperature as well as pressure. Okay, because whenever you are moving from this point to this point, your enthalpy is changing. Is this point clear? From this point to this point, when you have come, your enthalpy has changed or not? You have moved from some H0 line to H1 line. Okay, so your enthalpy has changed and pressure has also changed, temperature has also changed. So it means at high pressures, enthalpy is a function of both pressure and temperature for water vapor medium. Okay. However, if I go to very low pressures, in the low pressure zone, now you see, at a given temperature, the value of enthalpy is what? Line is horizontal. So this entire line is having same value of enthalpy. And at this particular temperature also, the enthalpy is remaining constant. At some other temperature also, some other unique value of enthalpy. So it means that if I go for because if I keep on moving pressure lines over here, so I am moving towards the low pressure side. Okay. So now if you see at this pressure line also, at this pressure line also, enthalpy is same. So if temperature is constant, then enthalpy is not changing with the pressure. What it means? At very low pressures, enthalpy will be what? Enthalpy will be function of only temperature. Okay. Now, limit of operating temperature I have given as 0 to 50 degrees Celsius. Corresponding to 0 to 50 degrees Celsius, my pressure comes close to 0.08 bar at 50 degrees Celsius. Okay. So it means if I test that these constant enthalpy lines where pressure dependence is reduced, if that pressure is less than 0.08 bar, then ultimately I can assume water vapor medium to be a what? I can assume water vapor medium to be a ideal gas where enthalpy is only a function of temperature. Is this point clear? So usually my pressure corresponding to this temperature is very low. In addition to that, there is one more constraint. Whenever water vapor will be present in moisture, it will not always be a complete vapor medium. It will be a mixture of dry air and moisture, water vapor. Okay, moist air. So the total pressure, which is typically ambient pressure, that ambient pressure will be made up of pressure of dry air plus pressure of the water vapor. Okay, and water vapor maximum can go up to which pressure? Its saturation pressure. That is limited by 0.08 bar. So it means that at low pressures I can assume even for water that enthalpy is purely a function of temperature. However, it is applicable only when water is in the gaseous state, because I am pointing only to the vapor phase, I am not going into the liquid phase. Is this point clear or not? Anyone is having any confusion about this? So in our air conditioning applications, mostly moist air will be having ambient pressure, and corresponding to ambient pressure, the pressure of water vapor will be very small, because mostly moist air will contain significant amount of dry air. So dry air will be contributing to larger portion of the pressure, and very small pressure will be contributed from the water vapor. Okay, and we know that ideal gas equation is valid either at extremely high temperatures or at very low pressures. Okay, so in this scenario, temperature for dry air, what is the condition? For dry air, pressure is significant, but the temperature is significantly larger than the critical temperature. Whereas for the water vapor over here, the temperature is less than critical temperature, but pressure is very low. So very low pressure is making the ideal behavior. Anyone is having any doubt up to this? Now let us consider that I have Ma as the mass of dry air and Mw as mass of water vapor, and this together is forming mass M, which is mass of moist air. Now you tell me what will be M? Ma plus Mw. All are clear with this point? Similarly, if I write the total pressure P, it will be nothing but pressure of dry air, air pressure plus, so total pressure will be equal to dry air plus pressure of the water vapor. Okay, so this pressure of water vapor is something which is called as partial pressure of water vapor. What we will be calling it? Partial pressure of water vapor. And this partial pressure of water vapor can have some maximum value. What will be its maximum value? Do you know the term vapor pressure? What is vapor pressure? What is the difference between partial pressure and vapor pressure? Please tell me. I have taught this in fluid mechanics as well. Any one of you? Any idea about partial pressure or vapor? Partial pressure is clear or not? Just now I explained to you that if I segregate the gases and if I allow a particular component to expand in entire volume V and at same temperature T, then whatever pressure it will be applying, that is its partial pressure. Okay. But what is vapor pressure? What is vapor pressure then? Tell me. Yes. When water, liquid of a substance is in equilibrium with the vapor of the same substance. So it means you can assume a situation. This is a room. In this room, if temperature is 25 degrees Celsius and there is no dry air, only I have liquid water at the bottom and at the top I have pure water vapors. Okay. So if initially there was no water vapor, pressure initially will be 0. When small evaporation will start from the liquid pool, then vapor amount will keep on increasing in the room. That will keep on increasing if vapor amount is increasing, pressure which vapor is applying on the pool, that will keep on increasing. Okay. There will be a limit after which, of course, evaporation does not stop, but after which whatever evaporation will be taking place, equivalent amount of condensation will also take place. Okay, equivalent amount of condensation will also take place. So that limit is called when vapor medium has come in equilibrium with the liquid phase. So that is the maximum limit up to which vapor will be present. So the maximum amount of pressure that vapor can apply is something which is called as the vapor pressure. What is PVW? Vapor pressure of water, and at vapor pressure both liquid and vapor are in equilibrium. It means state is this. Liquid will be corresponding to saturated liquid phase, vapor will be corresponding to saturated vapor phase. Is this point clear? And if I have to determine this pressure, then how I can determine? I can simply refer my steam table and I can determine the saturation pressure at the given temperature. Is this point clear or not? These are very basic fundamentals and you must understand actually. Otherwise, you will not be able to relate how we are solving for moist air. Okay? Is this point clear or not? So total pressure is sum of air pressure plus partial pressure of water vapor. But the capacity of water vapor to get maximum absorbance, maximum amount of vapor formation is limited by some pressure which is called as its vapor pressure, and value of vapor pressure is nothing but equal to saturation pressure at given temperature. Is this point clear? So it means that the value of partial pressure PW will always be less than equal to PVW, which will be equal to saturation pressure at the given temperature. Is this point clear or not? All are clear about this point? Now it means that if I have to refer to the vapor pressure, then I will be simply taking the value of saturation pressure at the given temperature. Is this point clear? However, this is very correct if I am having pure liquid and vapor of a same substance will be present. Okay. But if I have water vapor present, above water vapor I have dry air and water vapor molecules, then air molecules typically has tendency to increase the escaping tendency of water vapor from the liquid pool. Is this point clear or not? What I am saying. So whenever water vapor molecules are present in mixture with the dry air, then typically, so your assignment is completed now. Assignment only you are preparing. Huh? So what I am saying is, when water vapor is, please listen this statement again. When I have dry air generally increases the vapor escaping tendency. Okay. So in addition to the presence of pure substance, along with the dry air, more amount of water vapor will be forming. What it means? It means that whatever vapor pressure I will be referring from the steam table, that will not be correct one. Okay. The actual vapor pressure P dash of VW will be slightly larger than PVW, which is P sat at given T. Okay, so there is a correction factor F which is introduced. So P dash of VW is generally given as F times of PVW, where F is a correction factor for vapor pressure once it is being measured for what? Tell me. Yes, once it is being measured for water vapor present in dry air, present with dry air, present in moist air. Is this point clear? And usually the value of this factor is always greater than 1. And this factor is something a function of temperature. So you can refer to your textbook where you will be finding a table which gives the variation of F as function of temperature. Is this one clear? Anyone is having any doubt about this? All are clear about this? Now this is about the pressure. Now let us continue our discussion on enthalpy. Over enthalpy, first point we understood that at very low pressures, which typically are present in case of moist air, enthalpy of water vapor can also be made directly a function of temperature. Okay. However, one important point is that in moist air, this water vapor will always be present in which phase? Gaseous phase. Okay. That's why HWT equal to HGT will be nothing but HF at T plus what? It is in the gaseous phase. HFG at the given temperature plus what? Some enthalpy H dash in the gaseous phase. Is this one clear or not? See, if you have a substance over here, first you will be having liquid enthalpy up to saturated liquid point, then saturated liquid to saturated vapor HFG, latent heat of vaporization. Then from this particular state to this state, again there will be some sensible energy. Okay, so that sensible energy I have written as H dash G as T. Is this point clear or not? Now first point is at T equal to 0 degree Celsius we have set our reference state. All are clear about this point? So at T equal to 0, HF must be 0. HF must be 0. Okay, let me stop at this point. We will discuss further in the next class.